Now we start with space topics because I think besides me, there also will be some other people who wonder that someday Estonia will send up into orbit its own sentinels. And this is exactly what Rauno Gordan from Tallinn University of Technology is going to talk about. So Rauno, the floor is yours.
Hello, thank you very much, and thank you for inviting. I hope you can hear me. I will now try to share my slides. So I have been working in Tallinn University of Technology, and for the last 7 years, we have, 7 years ago, we started the satellite project to make small student satellites, to make one at first. And along the way, we got a very good chance to send to orbit actually 2 satellites. So this project from the very beginning was about, our idea was to make an Earth observation satellite. And there is a thing called the CubeSat standard. It's a CubeSat. So it's a 10 centimeters long cube. The satellite, our satellite weighs 1.3 kilos. And this was meant for Earth observation. And so during around 5 years of building, developing all the subsystems, we were able to complete 2 satellites. And the first one was launched to orbit in 2019 in the summer, and the second one was in last September. So as you can see here, this is the physical format of the satellite, which was handed over to our launch providers in 2019. And you can see 2 cameras, the holes there, the larger holes there. One is RGB camera, and the other one is near infrared. So we are using 4 channels altogether to capture images of the Earth. Now, the particular orbits of our satellites is, you can see here on this image of the Earth, is our 2 satellites. In Estonian, they're called Koit ja Hämarik. In English, what's the first one? Dawn and Dusk are the names of the satellites. And they were sent to sun synchronous orbit, which is very often used for Earth observation, so that they are able to cover with images the whole Earth. And they are at low Earth orbit, around 500 kilometers. One of them is slightly higher, the other one slightly lower, and they were sent there by completely different rockets from different cooperation partners. The first one in 2019 was by Roscosmos, Soyuz rocket, took it to orbit. And it's a large rocket. On this particular rocket were many other satellites, a large Russian weather satellite that weighs many tons, and then a lot of smaller nanosatellites. And our second satellite, Hämarik, was launched last year with Arianespace Vega rocket, a much smaller, but still was dedicated mission for small satellites. There were over 40 small satellites on board that rocket. So all of these small systems are dispersed in the low Earth orbit around and flying at astronomical speeds. So this Earth orbits of our satellites, they will get close to each other sometimes during near the North Pole and also near the South Pole. And they are at each particular illumination angle, so that the sun doesn't shine directly from above, but for one satellite, the images are so that sun is from one angle, and the other one, the sun is from a different angle, almost opposite angle. And so these are the orbits. This illustration is about what is our viewing angle. So when we're looking down with our Taltech satellites, Daltec and Datel satellites. So Datel has been our cooperation partner of making these satellites. And so looking down with the camera from this 500 plus kilometer altitude orbit, it's the image size is like what you see in this triangle here. And we would be able to capture an image with a size of around 100 kilometers. So one 5 megapixel image would be around one county size. That's our design system. So as I mentioned, we use 4 channels. And on a very small satellite, we're using X-band downlink, which is on 10 gigahertz frequency. And we noticed that this has not been used in such a small satellite before. So we're making some innovation here. We also tried to do some crypto experiments and some other computational experiments on the satellite. But at the moment, the software is not yet ready. We are able to upload software to our satellites. And so far, the first satellite has been orbiting for almost 2 years. And the sample pictures that you can see here are something that we would like to see, but we don't yet get our own images. So the satellites, we have regular contact with the satellites, but the software is not yet ready, and we need a lot of work to do so before that they can fully be functional. Some image of the insides of our satellites. You can see on the left hand there, or at first, the overall picture is about how the satellite will deploy wings, and on the wings you can have more solar panels, so you have much clearer, or you have much better, much more energy available. Otherwise, we have quite fast processor on board the satellite, and this will deplete the batteries in a couple of minutes. But as we can charge, have more energy, and only focus on taking pictures in certain parts of the Earth, and we don't have the continuous energy available so that we can fully cover the whole Earth. That's also a situation here. So on the left side, inside the satellite, you can see a radio system. Then next to that, the green are batteries. There are 4 lithium-ion cells. The middle system there, attitude control. This is controlling where the cameras are looking at. So we need to point the cameras towards the Earth, and preferably to a very precise location where we want to take the images. And you can see the cameras there, which take the full length of the satellite. And also the computer board is on the right side. So that's how it looks like. And all the subsystems inside the satellite, our teams in the university, working, majority of them students, were making them completely on our own. And we didn't buy in from other manufacturers complete subsystems. So also a big part of that is if you want to do 10 gigahertz communication and maybe achieve up to 1 megabit per second data speed, then you would also need a pretty big antenna. And this antenna we're also able to do in our own team. And right now it is tracking our satellite. There's a webcam that shows that, well, it's pointing to one direction or the other, so we can check if everything works in the right direction. But what are the other next steps, what we can possibly do, and some future ideas? So at the moment with our satellite project, we hope that our satellites will maybe work during 1 year, so that we can achieve, make those software ready. We can upload the software, and we can actually get from our own Estonian satellites some Earth observation images. So that will be a very good goal. Now, at the same time, we're also looking at what would be the next projects and who would be the cooperation partners for us to do the next projects. Because we are interested in Tallinn University of Technology to continue and grow our experience with space technology. And because it's a very practical field, then you would really need to do something. And after several more years, we would like to send to orbit the next satellite. So we're looking at cooperation partners. And Earth observation would be a good thing to do, as I think all of you agree with me. But really, the bottleneck is the communication, and probably we'll also be doing a CubeSat, either a 3-unit satellite, maybe a 6-unit satellite, but like maybe 100-kilo satellite will be out of our reach, depending on funding and cooperation partners. But forced communication is necessary on X-band, maybe on S-band, if we're able to use commercial frequencies. But Estonia, as a country with a good effort in cybersecurity, we would like to do some cybersecurity features there as well. Maybe carry some cybersecurity exercises on board the satellite, the physical satellite in space that has some subsystems that can be hacked. And there are a blue team and red team. One is attacking the satellite, another one is defending the satellite, and carry out this exercise. That's one way how to raise our experience with cybersecurity systems. So, and we don't know yet if we can do encrypted communication. Otherwise, right now we are using amateur frequencies, and we can get amateur frequency licenses from International Telecommunications Union much more easily than commercial frequencies. But amateur frequencies, you cannot encrypt. All the data that you transport needs to be public. You need to also publish the protocols. So anyone can go to your website and see what kind of protocols you're using, and if they have an antenna, they can easily intercept this data. So can we use encrypted communication? Depends on the need, depends who wants what. But if we want to do some cybersecurity experiments, exercises, then identification is necessary, a very secure identification. If we can't encrypt the data, at least we need to identify very clearly that this is our satellite that is sending us this data. It's coming from space, from that location, and also from the ground. That is our ground station that's giving it the commands. It is not somebody else, not taking over our satellite. So identification is what we can do. And maybe one solution is an ID card. At the moment, on our 2 satellites that are in orbit, there are Estonian ID card chips, and there's still lots to do in software to be able to do some experiments so that our own satellite would send an image from space with our this electronic signature made by the ID card. So we also try to get there. We'll see. So maybe that's one way for identification, just an idea that I'm trying to throw at the wall and see what sticks. And maybe an information system like the X-Road can be utilized and promoted even more, which is a secure and strongly identified way for sharing important data. So these are some of the ideas for communication and security. But what are some ideas for the physical modalities, how to take images? I've seen that these Sentinel satellites, if we're talking about optical data, they have a few channels, but maybe we can have much more channels. Maybe so-called hyperspectral imaging can be done. And there are some companies that sell these cameras for drones for hyperspectral imaging. You can have tens of layers in the same visual spectrum from the visual range of spectrum, but much more thinner data layers, so that you can distinguish between 2 green colors, while a human eye cannot do that. But in hyperspectral images, a machine can do that easily. Or tens of layers, or maybe even hundreds of layers in the visual spectrum. It's possible. Another idea would be to use some other modalities. Of course, there is SAR available, and we are not. I'm not talking here about SAR. Of course, this is also a system that we can try to start developing. But what about some other interesting ideas? And I've seen this kind of a product that is made ready, advertised to be put on airplanes, that does radio frequency imaging, but passively. This is not a radar, but it detects the passive radio frequencies that come from the background, from landscape, and they travel easily through clouds. So either radio spectrum or something that's between the radio spectrum and the infrared. There is something that's called terahertz. And terahertz images is used in airport security scanners. And usually it needs a strong emitter, a light source, and then the detector, a sensor on the other end. But it could be done passively as well. And while infrared does not go through clouds, terahertz already does go through clouds. So it's possible to do some optical range imaging, near optical imaging with like passive systems. So some other technologies that can be utilized to have small satellites that maybe we could afford to send to space, but would increase the capabilities. And there's a terminology called deployable optics, where you have a small satellite. At this case, on the left here, you can see this 6-unit CubeSat. So the shorter end is 10 centimeters, and the longer end is a bit more than 20 and a bit more than 30 centimeters. So this kind of CubeSat, but it's able to deploy a much longer telescope, like a telescopic lens, when it's sent to orbit. So it deploys when it's already in orbit. It has to move. There are motors and servos, actuators inside that make the lens move. It needs to extend to have a proper telescopic lens looking down to Earth. So that's the idea, is how to get higher resolution. Otherwise, our small cameras, which are at the moment on our Koit and Hämarik satellites, they might have a resolution about 50 meters per 1 pixel. In ideal case, if everything comes together correctly, or like 1 hectare per pixel. But with these deployable systems, it's possible to make much higher resolution with a very small satellite. So it might be an affordable way to create our own satellite for Earth observation with our own specific spectral needs, either this hyperspectral imaging or some specific channels, and maybe only take images of Estonia, Latvia, Lithuania, or some of our neighbors. And the data rate is always the bottleneck, the radio frequencies. And but then there's a next step to get even higher resolution. And these ideas might get into halfway to the spy satellite technology. So these are also small CubeSats here, imagined, drawn in 3D. And what you need to do to get high resolution is that you can only not have more magnification, more zoom. The images become blurry. But you need more aperture, you need wider lens. And most of these systems that are used in space, the space telescopes, they tend to be this reflector telescopes, the mirror. They use a mirror to concentrate the light. And if we can make the mirror wider, not just like the end of the 3U satellite, which is 10 centimeters by 10 centimeters, but we can extend that. For example, the image on the left, the mirror is 30 centimeters wide. It doesn't have to be a full mirror. It can have only sections. This provides enough light, but if the aperture is wide, if the mirror is wide, then you can have higher resolution. The images are not so blurry anymore. So this system also needs to be deployed, meaning that it will go to space in a rocket in the form of a cube, or in this milk carton shaped object. And once it's thrown out from the rocket, if it's alone in its orbit, then it can deploy the mirrors. And with this kind of system, if we are having this 30 centimeter wide mirror, it's possible to get the resolution down to 1 meter per pixel. So theoretically, this satellite here on the left could have a ground resolution of 1 meter per pixel. While look at the next image, and this one could even have like half a meter resolution if you can have the mirrors spread wider. But this is extremely difficult to do. And currently, I don't know any satellites who have used these deployable mirrors, because the mirrors need to be placed with like 10 to 50 nanometer accuracy. The actuation and placement of the mirrors need to be extremely accurate. The structure of the satellite needs to be really rigid and stiff so that it can keep those mirrors in the correct shape, correct alignment. And it's maybe it might be possible to do. There are in the labs, there are some works in UK and in Germany. I've seen some articles, scientific research that they are creating these systems in the lab, but I don't know any that have flown to space yet. So deployable optics, this is the large James Webb Space Telescope. This will also go to space either this year or next year. And well, this has deployable optics. The mirror is not complete when it's in the rocket. So it's in the rocket in a more compact form. So this will be sent to space, and then the large mirror will finally click to place to create like a 6 meter wide mirror. So this is an example of how this deployable optics really should work. So these are some of the satellite ideas. Another way how to get even higher resolution, and maybe with a smaller satellite, but when we use propulsion. So we have at the moment an interested party in Germany, a university. They create small, or their research project is about small rocket propulsion systems, ionic motors that can propel small satellites to faster speeds. And this idea is about that we should get closer to the Earth. Our small satellites now, the CubeSats, are at around 500 kilometer altitude. But if locally here in Estonia and Latvia and Lithuanian area, we could get closer, for example, to 300 kilometers, maybe even 250 kilometer altitude, then also the resolution would double. And with the same satellite, just use a slightly different orbit, which is an eccentric elliptical orbit, and to get closer to Earth here in Baltics and northern countries, and have a slightly wider orbit in the rest of the world. So maybe this is one way how to get with a small satellite but good resolution. So if you have any questions and ideas, you can ask me later that maybe some of you want to participate and point out some technologies that we can use, and then what should we really do. Next crazy idea is to not be in space but be in stratosphere. So this is exactly between the satellites and between the aerial photography and drone systems. So I'm at the moment taking part in this endeavor to create a system that stays in the stratosphere. So these are called HAPS, high altitude pseudo satellites. And it should be better from aerial photography in the sense that it flies much higher than regular airplanes, and it's easier to stay there longer. It's easier to keep the drone there at that altitude for many days and weeks. So the hourly usage price is coming down maybe 100 times, or maybe something like that. So it's reasonable to keep a system like that in the stratosphere, but it needs a lot of development. At the moment in the world, nobody has those things in the stratosphere yet, but there are many companies that try to do that. So this is one endeavor, and it's possible to put like much better cameras on the stratospheric system, 10 times better cameras, and it's 20 times closer. So if you like to have a close monitoring with down to like 10 centimeters per pixel imaging and constant 24/7 monitoring, then stratospheric system is the way to go. And also you can put SAR imaging on it, SAR radar systems, because this thing can travel in a straight line. The wind does not carry this away. You can you can create your own mission profile. So this is it. My talk about our nanosatellites and about some crazy ideas what we could do. So if you're interested in take part in this and have some ideas, then send some questions. So thank you very much.